Greetings, fellow teachers. My name is Tom Love. Welcome back to Basic Mathematics Using the Garden Approach. This session will be on cause and effect. Although cause and effect is a great topic for discussion in all the curriculum areas, mathematics, specifically algebra, looks at cause and effect as direct and inverse relationships. In this session, we will focus on direct and inverse relationships. We will look at their definitions, we'll look at the criteria, and look at the graphs of these two particular types of cause and effect situations. Well, let's get started here and look at cause and effect. All right, cause and effect develops critical and analytical thinking. Definition of cause and effect will be an event makes another event happen, or a variable affects another variable. Now, much work would give us, hopefully, much money. If we do a lot of food intake, then basically we're going to gain some weight. Why do things happen? And what causes them? That's something we always want to know. That's a human inquiry type situation, and that's what cause and effect takes a look at. Now, we've got a nice little simple situation here where we're going to look at the definition and some number pairs, all right? We're going to talk about variables, all right? And variable 1, if it goes down in value, then variable 2 goes down in value. So that is the definition that says if we're looking at two sets of numbers, and if one set consistently goes down and the other set consistently goes down, then it looks like they are direct related. If in another case variable 1 goes up and variable 2 goes up consistently, then it's likely they are direct related. Now, one other criteria is that the quotient of the investigated pairs, the one we're looking at, is a constant, all right? Now, we're assuming that we can always keep all other variables constant. That means we couldn't have a true investigation here if we have a third variable affecting 1 or 2, and we don't want that to happen. All right, now let's look at our data pairs here. All right, we can see that V1 is going down in value, and V2 is going down in value. Now let's look at the quotients. The quotient here is 3, 3, 3, 3, 3, 3. So that looks pretty good. It looks like it fits all the criteria for a direct relationship. All right, direct relationships are common events throughout the real world. They're constantly impacting our daily lives. Now, remember the ups and downs. Let's take a look at these. Let's look at some weather. If the temperature rises, then matter increases in size. Okay? That makes sense because that's simple physical science. Now, let's take a look at something about the body. If we decrease our exercise or don't do it at all, we're going to gain weight. All right. Now that does make sense too, but that certainly doesn't fit the criteria of both going up or both going down. And then finally in school, if we quit doing homework or we decrease drastically the amount of homework we're doing, it's more than likely our grades are going to go down. So these two are going down and these two are going up, and they both sort of fit the definition of a direct relationship. All right, now let's look at an isolated experiment and some numerical values. In this particular case here are our data pairs. Number 1, this particular first set of numbers, is increasing in values, and the product is increasing in value. That makes sense, okay? And N2, the second number of the product, is constant, and that makes sense too because 3 is held constant here. Okay, so it looks like if we're talking about N1 and P, the product, both of them are increasing, it's very likely that's a direct relationship. Now let's look at the quotient of the pairs of the numbers we're investigating. We're investigating number 1 and the product, and that quotient would be 3, 3, 3, 3, or 1/3, 1/3, 1/3, 1/3, whichever way you want to look at it, but the quotient is constant. Hopefully all other things, and in this simple experiment there is nothing else that would impact those particular numbers. So guess what? I'm making a very broad statement here and saying that N1 and P are a direct relationship. Now let's take a look at the graph. If we were to graph these data pairs, now remember we're graphing the product against the first number. And of course this would be 1, 2, 3, 4, 5, 6. Where down here we would be graphing 3, 6, 9, 12, 15, and 18. All right, now let's try a point here. If the product is 6, then number 1 would be 2, and right there it is, okay? If the product is 9, then the second number would be 3, right there it is. If the product is 12, then the next number would be 4. The number associated that would be 4. And if the product is 15, then the number associated would be 15 right there. Looks like we have a direct relationship, a straight line. Everything looks pretty good. That is what a direct relationship would look like if we were to graph it. All right, now, there is a very terrific formula that's very common and very nice to use when studying direct and inverse relationship, and it's distance equals rate times time. Okay? Now, let's say we're going to hold R, all right, and we'll vary D and T and see how they're related. All right, now time, we'll let it increase 1, 2, 3, 4 in hours. All right, rate will stay the same. Let's say we're traveling at 30 miles per hour. All right, let's see what happens here. Now, if I increase time, going at 30 miles per hour, 1 hour, I go a distance of 30 miles. 2 hours, which would be 60, 3 hours, which would be 90, 4 hours would be 120. So it looks to me like distance is increasing, so is time, so it looks like they are a direct relationship. All right, now what if I conversely held T constant and rate increase, which means I would go 30, 40, 50, 60, 70 miles per hour, go faster for the same amount of time. I'm sure you could see that right there, D and R would be directly related. Now, this is something nice that students get their hands on. It's a real life experience, and it's very much related to our simple little experiment that we looked at a little bit ago. All right, now, let's use MS Excel. All right, now these are just some simple directions on how to set up a direct relationship and have MS Excel graph it. Now, nothing wrong with graphing the way we did. Students can take a piece of paper, make a coordinate system, mark off the tick marks of it, and plot the points. That's excellent. That's hands-on. That's real-world experience as well as using Excel. All right, let's take our spreadsheet and start at B5 and enter the numbers 1, 2, 3, 4, 5 downward by just hitting enter. Then let's go right next to C2, and I don't expect you to be doing this, just following along and listening to me, okay? All right, then right next to the B5 at C5, let's enter the numbers 2, 4, 6, 8. Now note that the B's, we'll call them the B's, they're increasing 1, 2, 3, 4, 5, and the C's are increasing also 2, 4, 6, 8. All right. Now I want you to take your mouse and click and drag and select all the numbers. That means both columns of numbers there will be selected. All right. Now at the top of Excel, there's a little thing that looks like a graph. It's got some little bars on it, a little red bar, a little green bar. It's called the chart icon. Click on it, and you'll get some options. One of the options will be an XY scatter options. Click on that. Then you'll get some different images that come up. And these images, one of them will have some dots and it's a curved line. Click Finished, and voila, you get a graph of a direct relationship. It is a line. And again, why would it be a line? Well, primarily because the quotient of the data pairs is a constant, and if you investigate the order pairs, that's what you're going to get. And a straight line does have a constant slope when you get into mathematics later on, in heavier mathematics. Let's say we're comparing 2 to 1 here, we have a slope of 1. Always the quotient of the data pairs will be a constant, and that is the definition of the slope of a line. So that's why a direct relationship is a line. All right, now let's look at inverse relationships. Inverse relationships, now let's just look at the definitions. We're taking a look at two variables here. Variable 1 goes down, variable 2 goes up. Oh, they're going in opposite directions. Now, if V1 goes up, then V2 would have to go down. Again, in opposite directions. The product, not the quotient of the investigated pairs, is a constant. All right, again, this simple little experiment here, all other variables must be held constant. In a real-life experiment, that is probably the most expense in a real-life experiment when you really want to find out how two things are related, is to keep all other things from impacting the two that you're studying. All right, now V1 is decreasing in value here, where V2 is increasing in value. All right, that makes sense. One's going down, the other's going up. Now let's look at the products. Well, let's look at this one. This is an easy one. This would be 72. That's 72. Let's see, 32 and 40, that's 72. 60 and 12, 72. Looks like everything is 72. So the products is a quotient. So it looks like we have an inverse relationship here. All right, inverse relationships are common events throughout the world. They're constantly impacting our daily lives. Let's take a look at a few. Well, these are the same we looked at before, so we ought to get these pretty good. We knew that if temperature goes up, matter goes up, so that's no good. That's a direct relationship. Now let's look at things that affect the body. If we quit exercising here and our exercise time decreases, then our weight increases. Hey, we got an inverse relationship here, it looks like anyway. Now we got a lot of other criteria, but this is looking good. And of course, school here, if our homework decreases and our grades decrease, they're both going the same direction, so I can cross them out right away. The only one that looks like a possibility is that one that deals with the body. All right, now, a simple isolated experiment, again with numbers and a product. All right, now this will be N1 and this will be N2, all right, and this is our product. If N1 increases, yes it is, and N2 decreases, well, so it is. Do you see N1 is increasing in value or N2 is decreasing in value, and the product is constant? Well, sure looks like it is here, so it fits our setup pretty good. How are N1 and N2 related? That's what we're studying. Okay, so N1 is increasing, N2 is decreasing. Let's look at the products. Well, that's pretty obvious here. The product of the investigated pairs always give us what? 6. All others are held constant, so it sure likes N1 and N2 are inversely related. Okay, now let's plot the points. Now, it looks like we've got 1, 2, 3, 4, 5, 6 here, and likewise 1, 2, 3, 4, 5, 6 here. All right, if we plot the first point, if N1 is 1, then N2 would be 6. Here it is. If N1 is 2, then if N1 is 2, then N2 would be 3. There it is. If N1 is 3, here it is, then N2 would be 2. There it is, coming right up through there. How about that? And of course, if N1 is 6, which is right up here, N1 would be 1, right there. And notice we have a nice little curve for an inverse relationship, and everything works out pretty good. This would be the graph of an inverse relationship. Now, it's not this kind of a curve, but it's a kind of a curve that tends to go closer and closer to both the axis of the particular coordinate system we're graphing it on. All right, now a very nice relationship to work with, again, with either direct or inverse relationship, is distance equal rate times time. Now let's say we hold distance constant. Let's say we want to go like 120 miles. That's the distance we want to go. Now our rate is basically going to go from 30 to 40 to maybe 60 to maybe, let's go with that, okay? Now, what kind of time are we going to have? To get 120, we'd have to go 4 hours. To go at 40 miles per hour to get 120, we have to go to 3 hours. And to go at 60, we'd have to go 2 hours. Well, notice the time is decreasing where rate is increasing, so we have an inverse relationship. At least it looks like that. So we'd have to collect some data and investigate the products and graph it to really substantially say that this is an inverse relationship. Now, do you know any other simple formulas like this that would be very easily used as an example for studying inverse and direct relationships? I bet you do. Now, we have looked at qualitatively what inverse and direct relationships are, and we have also looked quantitatively as mathematics looks at direct and inverse relationships, and all this plays into cause and effect. So this is an excellent little exercise to help students understand these, and this would be helpful in the real world as they grow up as an adults and get jobs, or also it's very beneficial when they take those well-known standardized proficiency tests. Well, I hope you enjoyed this session, and looking forward to talking with you in the next one.